It works? Does it work? It works. So, okay, it's a great pleasure for me to introduce CHRISTOPH LEHNER today. We met, I don't know, how many years ago?
Quite a while now, at least 10.
10 years
I think it was around
20.
almost 20. Yeah, it was the Einstein exhibition. Yeah, 2005. 2005. Yeah, the Einstein anniversary. Yeah, true.
And at that time, you told us something about some new revelations about quantum entanglement and how early it was discovered, not by much before the EPR paper. You will tell us more about that. And I finally thought, you know, we should ask you to come here, and you are here now as a senior visiting fellow, which is very nice. And I hope you come again. We should talk about it next week, how we can arrange for you to come again. Maybe I can introduce CHRISTOPH LEHNER a little bit. Maybe first the education. You were a student at Stanford University, 1990 to 1997. The PhD thesis was already quite interesting. Reality of quantum mechanics, an interpretation of Everett's theory of the universal wave function. Very interesting. It's an interpretation of an interpretation. Very interesting. Very, very interesting. The advisor was Patrick Suppers at that time. Then you were at the London School of Economics with Nancy Cartwright, also very well known in the field. And before you got your diploma in physics at the University of Munich on the problem of energy conservation and phase transitions in the early universe. Started in the example of hybridization. So this was hardcore physics. Right?
That was my last real encounter with it.
Right. Your supervisor was Harald Fritsch, who was a very good friend of mine. And very early you also worked on Konrad Lorenz concepts and so on. Then I mentioned that after your stay at Stanford University, you had appointments in Kentucky. You were an assistant editor of the Einstein papers. You were at Caltech for the Einstein papers project at the Max Planck Institute for the History of Physics in Berlin, who at that time had a very good program on research in quantum mechanics. I understand that this is being faded out or has faded out.
Alas, yes.
Which I think is not a good idea given the many open questions in the field. But it might come again. And you were also a visiting fellow at the Hebrew University in Jerusalem. You have a number of very interesting grants by well-known institutions like the German Deutsche Forschungsgemeinschaft, the foundation of the Lindau Nobel laureate meetings, the German-Israeli Foundation for Collaboration, and some grants from the Max Planck Institute. Well, having said all this, I look very much forward to your talk today, and I'm curious to learn something new and learn the things from earlier again and deeper. Thank you very much. Thank you for being here.
Thank you very much. Yeah, I hope I have something new and interesting to say. Thank you very much for the invitation here to Vienna. I've been enjoying my time here very much. It's been very inspiring. And yeah, I hope something good is coming out of it. So today I'm going to talk sort of an overview about the research that I've been doing about sort of the history of the ideas of entanglement based on Schrödinger's notebooks. So just quick orientation. This I probably don't need to tell you, right? 1935 was an important year for quantum mechanics. It was the year in which Einstein-Podolsky-Rosen published their paper, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? Despite that title, I think we can now say that it's really one of the most important papers for modern research of quantum mechanics that really brought that problem up that, you know, we're still gnawing on, that's keeping philosophers unsettled and physicists busy. And also a little less well known, but also really important, Schrödinger's response to that paper, the current situation in quantum mechanics, in which really the term entanglement got coined by Schrödinger, right? I mean, that's really where the concept, where the word comes from, and which offers this really, I think, very deep and interesting discussion of what Einstein, Podolsky, and Rosen had proposed. It also has Schrödinger's cat, but I'm not going to talk about the cat today. So, the interesting question for the historian is where do these ideas come from? Because 35 was long after the, you know, big discussions in the early days of quantum physics, right? Both Einstein and Schrödinger had criticized quantum mechanics in the early years, 1926, 1927, and had criticized especially Bohr's and Heisenberg's interpretation of quantum mechanics. But then sort of things got rather silent for a while. And sort of it looks on first view like these papers in 1935 come out of nowhere. And so it's been a question that people have been thinking about for quite a while. What was really the story from these early discussions to the papers of 1935? So there's one step in the middle that, you know, historians have claimed is an important step on the way to 1935, and that was a thought experiment that Einstein proposed, never published, but only orally discussed in the Solvay conference of 1930, and that we only know really from then the remembrances of Bohr that he published much later in 1948 about the conversations with Einstein about this photon box experiment. So I'll talk a little bit more about that later. But so the hypothesis is that that was a precursor of then what Einstein did in 1935. But what really happened in the intervening years has remained mostly nebulous. And so my story now is based on the notes, on the research notes that Schrödinger left. There are really literally hundreds of them, folders, notebooks, bundles of sheets. And what's really unusual about them is how detailed they are. They're really sort of stream of consciousness prose in which Schrödinger really details his thoughts while writing. And we really don't have that from any other physicist in the time that I know, which means like from the late 19th to the mid-20th century. It's very unusual for a physicist to really sort of write down his thoughts as he's thinking, or she, of course. So it's very interesting material, but it's also because of the sheer mass of it a little bit hard to find your way through it. They're not usually dated and they're not chronologically ordered, so it's often like, you know, searching the needle in the haystack to find the correct thing. Also, you often have folders that have a certain title, but what's inside doesn't necessarily have anything to do with the title. But so if you dig through them long enough, you find some good things, and that's what I want to talk about today. So the two main points that I want to talk about is how Schrödinger even came across the problem of entanglement, and then how that then played out in the story leading up to EPR and Schrödinger's response to that. So first we start early. you know, Schrödinger developed wave mechanics in very short time in the winter 1925 to 1926. I mean, it really happened within the intellectual breakthrough really happened within weeks. In the November of 1925, he finally got hands on the de Broglie's dissertation, which introduced this idea of matter waves, and within basically a couple months, he had already formulated the first publication on wave mechanics. So this was for him, of course, you know, sort of the moment of great intellectual success, and it started really before he even encountered de Broglie. Right, Einstein pointed out de Broglie to Schrödinger, that he reinterpreted the Einstein-Bose statistics as a statistics of waves. Right, Einstein and Bose had sort of introduced this new statistics ad hoc, just, you know, justifying it by its success in explaining the Planck distribution of wavelength in the radiation. And Schrödinger realizes, you know, we don't have to, like, you know, introduce ad hoc this new statistics if we talk about it as a statistics of waves. And this was especially interesting because one of Schrödinger's early, or the things that Schrödinger was thinking about there was the gas statistics of, the quantum statistics of ideal gases, right? There was no good explanation for the Nernst law. Everybody acknowledged that it must have something to do with quantum theory, but nobody really had an idea how to quantize an ideal gas, because old quantum theory could only operate with periodic systems, right? There was no good idea what to do with material particles flying around, and how to make a quantum theory of that. So Schrödinger realizes, if we think of these particles flying around as standing waves in a box and quantize that, then we get Bose-Einstein statistics, and then we can explain the Nernst law. And that really brought him to understand, you know, to the idea of wave mechanics. He immediately goes on to generalize de Broglie's idea to set up a general wave equation for matter waves. And for that, a really important point is this idea of the Hamiltonian analogy between ray and wave optics. This idea that you can sort of translate between a story of trajectories of particles and a story of wave fronts in a medium. And so that really helped him to, you know, go further than de Broglie had gone, get to the wave equation, first the relativistic and then the non-relativistic one, and sort of, you know, explain the Bohr model on the basis of this wave equation. So all this, I'm just telling you to show you that really sort of the fundamental idea behind all of that is that matter has a wave nature. And this was sort of really stuck with Schrödinger. And so one of the central motives that you see coming up again and again was that he protested against the interpretation of quantum mechanics as a theory of particles. And if you see, basically everybody else in the early days thought of quantum mechanics as a new statistical theory for particles, right? Einstein was very much enamored in the photon model, right? I mean, this was like one of his early ideas. And Heisenberg had sort of this idea that, you know, not just Heisenberg, but also like the whole Göttingen crowd, like Born and Jordan, that it really was sort of a generalization of analytical mechanics, right? That we had this direct translation from analytical mechanics into quantum mechanics. And so the basic intellectual model for pretty much everybody but Schrödinger was a theory of particles. It was a new theory of particles, but somewhere in the background were still the particles. And Schrödinger was really sort of the only one in the field that clung to the wave picture, even after, and I'll get to that in a moment, it showed that this was, of course, also very problematic. So very early on, right, 1926, in the summer of 1926, Schrödinger already shows that wave mechanics and Heisenberg's matrix mechanics are translatable into each other, right, that they're basically two aspects of the same theory. And so it's now not that we have two theories of the atomic structure, but we have one theory with two absolutely different interpretations. And that's really where the interpretation debate begins, with these debate between Schrödinger and Heisenberg. And it has basically two sides. One is a general methodological side about Anschaulichkeit, right, intuitiveness, visuality of models, right. I've talked about that in May more, so today I will not talk about that. And the question of continuity versus discontinuity, right. What Schrödinger thinks is that with wave mechanics he can get rid of the quantum jumps. He can really have a theory that gives through-going continuous processes that explain physical processes, whereas the Göttingen crowd, Heisenberg and Born, insist that this you cannot explain all the discreteness of quantum jumps that had been observed since 1905, the latest, away by reinterpreting this now as continuous processes. And to show this, Heisenberg, no? Why does this not? Here we go. No? Yeah. To show this, Heisenberg publishes a short paper. This is sort of a corollary to his papers about the spectrum of the helium atom. He considers the energies of two coupled oscillators. And he has a very simple argument to say that these two oscillators can only be in the eigenstates of their energies, right? He thinks of two oscillators with two energy levels, En and Em, right? And they're coupled by a weak interaction. So there is a transfer of energy, of course, between them. But now he does not consider sort of the energy eigenstates, but he tries to say something about the energy of each individual oscillator. And that, with a means of matrix mechanics back then is still rather difficult. So he makes a very general argument. He can calculate what he calls still time averages, right? What we now would call expectation values for the energies. And he says he can easily derive that the expectation value for each single oscillator is the average between the two energies, the two energy levels. But he can also show that for any function of the energy, so say the square of the energy, any nonlinear function, the average will also be, the expectation value will also be the average of the two expectation values, of the functions of the two energies, sorry. So the expectation value of the energy, of the function of the energy will be the average of the functions of the energies of the two oscillator. And this, you can easily see, right, if you have a general function, right, if it's, say, if it's convex, can only be, right, if the energy is always either En or Em, right? If it's something in between, if there's a continuous transition, then the averages will not simply sum up. And so there cannot be, Heisenberg concludes, a continuous change of energy, right? The energy of each oscillator always has to be either En or Em. And in hindsight, right, this is not surprising, right? I mean, obviously, if you think of a weak coupling, the eigenstates, the energy eigenstates will not be changed much, right? And so, yeah, there won't be any intermediate energy states suddenly. But back then, this was still, new and interesting, and especially sort of very problematic for Schrödinger, because then, of course, according to his ideas, the energy should be flowing continuously between these two oscillators, like in the classical case. So Schrödinger tries to argue against it, and he tries to understand what's going on there by like now sort of retracing Heisenberg's argument in wave mechanics in his formalism. And there is 2 big notebooks about that called Undulatory Statistics 1 and 2, right? He sort of tries to get these statistical statements out of his wave theory. And in the very beginning, there's this wonderful quote that sort of describes the central motive of his thoughts. And it says, I mean, what you see here is Schrödinger's Gabelsberger shorthand, right? His stenography that we talked about the other day, that unfortunately I still am not able to decipher, but luckily this has been described before, so I can understand this part. And it says, averaging over the phases has to completely replace the statistical obscenity from Göttingen, right? So, to get rid of these the claims of the statistical nature of the wave function, he tries to sort of now use the arguments from you know, in the tradition of Planck's derivation of the Planck law from, you know, the wave nature, really a consideration of a statistics of waves by averaging over the phases. He wants to get back the statistical claims of the Göttingen crowd. So he already has developed perturbation theory at this point, right? I mean, there has a perturbation theory for wave mechanics, so he just, you know, treats these oscillators with perturbation theory and tries to get a dynamical model for the process. But very soon, here's another quote. So he's trying to calculate the transitions between the 2 states. We will calculate these beats, right? I mean, the transformations now are beats between the 2 oscillations of the oscillators, and we'll find that really the perturbation matrix and the transformation velocity are connected. But if, after all, there really are slow transformations, how can it be that in the case of reaction degeneracy, so, you know, these 2 equal oscillators, Heisenberg could get his strange result with as-if discontinuities. And soon he comes to an answer. Well, obviously, because the joint oscillating states that appear immediately with the interaction are of such a kind that they cannot be dissolved into states of the single system. So, obviously, right, he comes to states that are defined in the higher dimensional, right, in this case, 4-dimensional space of the 2 oscillators, and not in, you know, a simple 2-dimensional state that he could interpret as resolvable states in you know, that can be ascribed to the individual oscillators. Worse, it seems, even if one applies the interaction slowly and stops it again, the remaining oscillating state will be of the above-mentioned irresolvable kind, right? This problem even persists after there's no interaction at all anymore. So, we know, of course, well, der besprochenen nicht auflösbaren Art sein wird. Nicht auflösbaren, ja. So he makes a little diagram of the energies, right? But couldn't the matter still be understood thus that in both systems, both energy levels remain excited, right? If they're both excited, then, you know, the average energies could be somewhere in between. But no, we obtain the result, right? That, you know, always the only parts that come into the dynamic development are the ones where one is excited and the other one is not, right? The other 2, right? The other two combinations have different total energies, and so obviously it's impossible to get them by a temporal evolution from the original state. This is all summer of 1926, right? This is his direct response. Heisenberg published that paper, like I think in July 1926, and as I said, they're never dated, but this is immediately the response to that. And Schrödinger actually publishes a response to it, in which he totally does not mention these problems, right? In which he very confidently announces still his position that this all can be explained by continuous processes, but as you see from the notebooks, he's already realized no, he cannot, right? So and this is really his first encounter with the problem of entanglement. He doesn't call it entanglement anywhere here, right? It's this still sort of these descriptions of the unauflösbare Zustände, but obviously that's what really causes him a serious problem in his interpretation. So the debate continues still for quite a while, right? I mean, basically, most everybody else is not convinced. Even sort of the old guard that first was very excited about wave mechanics, right? Einstein, Lorentz, Sommerfeld, all are very sympathetic, basically, to his point of view, but they all start, start pointing out that the fact that his waves are defined in configuration space and not in physical space really makes it impossible to see them as a sort of a physical wave in the sense that Schrödinger originally envisioned. So in 1927 at the Solvay conference, right, the famous one where sort of the positions were all formulated, Schrödinger presents his wave mechanics and sort of takes a last stance for his interpretation, but even Einstein at this point already criticizes this idea that the wave function could be some physical entity in the sense of a classical wave. And so basically Schrödinger has to give up. Einstein then veers in the direction of de Broglie and thinks we should try a theory that combines particles and waves in the sense that de Broglie originally envisioned. Schrödinger still holds out for a few more months, but by the end of 1928 he publishes a paper in which he sort of also admits that it's simply not possible to reduce all the quantum effects to a continuous wave theory. And in 1928 there's also experimental results, right? Enrique Gaviola, an Argentinian physicist that was at that time in Göttingen, did research on the emission of on the fluorescence of substances, and shows that the emission of radiation has a time character that's described by the exponential change between states, and not like what you would expect from Schrödinger's beaten model, right? That it sort of has to build up slowly, right? Because in Schrödinger's idea, when we have an excited state, at first there is no interaction between the excited state and the ground state, because there is nothing in the ground state, right? There is no excitement in the ground state, so there cannot be any interference, right? So some external disturbance first has to excite a little bit the ground state till a beat between an interference between these states can happen, and it's interference that then causes the radiation. So the time profile will be a very different one than this idea of Heisenberg, that sort of spontaneously the emission starts and then sort of happens with an exponential decay. So basically Schrödinger's original ideas failed, but he's learned a lot about entanglement in the course, and that is my argument will now come in handy in the second part of the story. Schrödinger sort of at this point And this sort of remains his position till the end, right? He admits that his original ideas about the wave nature of matter don't work, but he still is not happy with the alternative, the sort of what we now call Copenhagen interpretation, Bohr's idea of complementarity, the idea that we cannot have any intuitive and really logically consistent model of atomic processes. He insists that there must be a better story that can be told about quantum mechanics, even though we don't have it yet. And so the further discussion between Schrödinger and the rest is, and there again he meets with Einstein, who sort of has the same position. Yes, for the time being, quantum mechanics is the best thing we have, but we cannot be content with it, right? That cannot be the end of the story. It's too illogical, it's too self-contradictory to really be a satisfying physical story. So the one evidence we have of that is as I said, this photon box story of Einstein in 1930 that, as I said, Einstein never published, but the basic idea is you have a box filled with light, and you have a shutter on it that opens very quickly to just let out one single photon, however that might work. And then, after that happened, we can do two things. We can either weigh the box, right? And by this change of the weight of the box, right? We weighed the box before and now we weigh it again. So by the change of weight, we can figure out how much energy was lost. So we can determine the energy of the photon that went out. Or we can measure the time when the shutter opened, right? And with that, since we know the velocity of light, we can determine the position of the photon. So we can do both in contradiction with the uncertainty relation. And sort of just by measuring the time of the opening of the shutter, right? Because light has a constant velocity, so we will always know how far it's gotten since then. So then Bohr has an argument. He needs to invoke general relativity, why those two measurements cannot be simultaneously performed, and thinks by that he has given a good answer to Einstein.
But there's a proof, I think, about 20 years ago, I think Shimoni or somebody like that, who showed that you can argue without general relativity.
Yeah?
You still win against that.
Yeah. The question is just, right, the interesting question in our story is that Don Howard in 1990 claimed what Einstein really wanted to argue here was not that you can measure these two simultaneously, but that you're free to measure one or the other. And so it is already, according to Don Howard, a precursor to the Einstein-Podolsky-Rosen argument, right? Yes, we cannot measure both things at the same time, but since the photon is long gone once we do the measurements, right, depending on what we measure, right, we determine non-commuting quantities on the photon, right? So the argument is, since we can measure either one, they must both exist. So we don't know, because we don't have any written record besides Bohr's account, right, which didn't read it that way. But it's not implausible, and there is a piece of evidence that after the discussion, there is a letter from Ehrenfest to Bohr in which he says Einstein has by no means invented the weighable light flash box contra uncertainty relations, right? So Ehrenfest at least understood it in the way that this was not supposed to be this argument that Bohr thought it was. So this is Don Howard's basic argument, right? That he's already accepted that the two measurements cannot be both performed, but already the possibility that we can measure either is for Einstein an argument why quantum mechanics doesn't tell us the full story. The photon has both an energy and a position, and so, or a momentum and a position. So they must both, since we both can measure them, they both must have a definite value. But, you know, still it's surprising Einstein doesn't say anything like that till 1935. And if that was the argument, it is sort of, yeah.
How does he understand this? Why keep the uncertainty relations? I mean, how can you both have the uncertainty relations and both non-commutative observable stuff?
Well, the idea is, right, you have the uncertainty relations as a restriction on measurability, right? You cannot measure simultaneously, but that doesn't mean that they cannot both exist, right? So it's just our inability to measure that the uncertainty relations describe, not the non-existence. And that is basically the bottom line of the argument in EPR in 1935. So it's not implausible that this was already an idea there. But as I said, we have nothing from Einstein that clearly expresses that. Now, there is an interesting hint in the correspondence, you know, the correspondence of Schrödinger and Einstein after Einstein published EPR in 1935. And so this is the very first letter that Schrödinger writes to Einstein in 1935 after the publication. And he starts it with, I was very pleased that in the recently published work in the Physical Review, you have also publicly grabbed the dogmatic quantum mechanics by that coattail about which we already had discussed so much in Berlin. Now, this translation is a bit clumsy, right? I'm not quite sure how to translate Schlawittchen into English. But the important thing is that he says, by that point, right, you grab the quantum mechanics by that point, which we already back in Berlin discussed so thoroughly, right? So very clearly, right, that sounds like the argument was already known to Schrödinger from the time before they both had to leave Berlin in 1933, and that they'd already extensively discussed this case. And so the question is, can we find any traces of these discussions? And I claim we can, right? I think we found several manuscripts in Schrödinger's papers that have a direct bearing on that. And interestingly, they are under the strange, still to be explained title, Szilard-Spiegelversuch, so Szilard mirror experiment. And the mirror experiment very clearly is, we can see here, right? This is one, obviously the first manuscript to that, because it's sort of the most spontaneous and non-elaborate. And so Schrödinger makes this little sketch. There's a Spiegel here, right? There's a mirror here with a mass m, and there's a light quantum here. And in the text, then Schrödinger explains, right, how this is supposed to be working, right? The mirror originally is the position 0, but the position is very uncertainly determined. We've measured very precisely the momentum of the mirror, right? So the momentum is very precisely determined. The position is rather undetermined. With a light quantum, it's the opposite. There we have very precisely measured the position and very imprecisely the momentum. Now we let the photon reflect from the mirror. And the claim is that afterwards, by a measurement on the mirror, we can either determine the position of the light quantum or its momentum, and both with high precision, right, with precision that's higher than the uncertainty relations would allow to us. There is a second, much more elaborate manuscript, which starts, and that gives us a wonderful context and date for this whole thing, right? One of the few manuscripts that Schrödinger actually dates, right? It says 4th of November, 1935, no, 1931, sorry. And it starts, it is about the following question posed yesterday by Szilard in the colloquium. So there must have been a colloquium in 1931. And question is if we kind of unfortunately, yeah, and if he says colloquium, then the plausible conclusion is that it was the famous Wednesday colloquia at the Berlin University, right? That was the sort of the big meeting of the physicists in Berlin at the time. And unfortunately, there is no like records of those, right? We don't have any like list of events for them. So in the end, I mean, these were very spontaneously organized things that were not really in any way well documented. But in this case, we're lucky. Oh, where am I going? We're lucky that we actually have a printed summary of the fact that Einstein on the 4th of November 1931 in the Physikalische Kolloquium gave a talk über die Unbestimmtheitsrelationen. And in this talk, you can see there's a brief summary. What Einstein presented was exactly this photon box model that I talked about earlier. So even though there was never a written account of it by Einstein, Einstein presented it there in the colloquium. So there was a colloquium, we have the time and the date, and it must have been in the discussion afterwards that Szilard presented this idea of the mirror. And we have actually what we only found afterwards, which is sort of an embarrassment. There is a letter from Schrödinger to Sommerfeld in which he tells exactly that story. So we could have started with that, of course, if you had like studied the letters more thoroughly. So I'll read you that letter because it gives a nice brief introduction, summary of the ideas. He writes to Sommerfeld, "The foundational problem torments me more and more, unfortunately quite unfruitfully. In the seminar, we have discussed the following actually quite simple case for hours. So initially, we very accurately measure the momentum equals 0 of a heavy mirror in the position of a photon. Then let the photon reflect on the mirror, and then he tells, the further story. After the photon has separated some distance from the mirror, we have the choice by a measurement on the mirror to determine either the position or the color, i.e. the energy, i.e. the momentum of the photon. Because the photon has nothing to do with the manipulations on the mirror, one can hardly say that its sharp position or sharp momentum is only created by one of these manipulations. In any case, this is not a creation in a real, but at best in a mental sense. One would like to conclude that the photon always possesses a definite position and momentum. Right? This is exactly then Einstein's conclusion in 1935, a view that we have long ago abandoned as paradoxical, right? Which is in contradiction with what we've learned from quantum mechanics. The only way out, it seems, is by something like this emergency decree. In quantum mechanics, statements about what is real, about the object, are forbidden. This "they" is a bit strange. I mean, quantum mechanics deals only with the relation object-subject, and apparently in a much more restrictive sense than in any other description of nature. Right? So basically, the only way out from this dilemma that Schrödinger sees without giving up quantum mechanics is to say we can basically not say anything about what's happening between the two measurements. Right? We cannot give any good physical story. We can just sort of report the statistical connections between observations. Brief excursus, Leo Szilard. He's not that well known, so let me give you a very quick look at him. He was one of the so-called Martians, right? A group of incredibly talented young Hungarian Jews in Berlin in the 1920s, right? John von Neumann, him, and Eugene Wigner. And he has a really interesting story because he first studied engineering, and even though he was a theoretical physicist, he always had this, he was always incredibly close to questions of experiment and technical feasibility. So one famous story is that together with Einstein, he constructed a refrigerator that has no moving parts, and they got several patents for it. It was never built, but they were very seriously working on it, and he actually has lots of patents in his names. For example, he has a patent for the nuclear chain reaction, which he conceived of long before nuclear fission was discovered, already in the early 30s. He already had that idea. If you can find a nuclear reaction that produces enough neutrons, right, we can then use these neutrons to trigger more nuclear reactions, and so produce a chain reaction, and with that produce lots and lots of energy. So that is one reason why then in 1930, was it 30? No, I'm not quite sure, 39, when was nuclear fission discovered? Whenever it was discovered, right? When you heard about it, he was immediately aware that this was exactly that kind of a reaction. And so he was really one of the first people that recognized the potential of this discovery. And that's also the reason why then he got Einstein to write this famous letter to Roosevelt that was really his letter that Einstein just saved. Right? Some other things that he did, he's already conceived in the 20s of the idea of an electron microscope, right? Had also a patent for that, never pursued that any further. He had like, you know, an early process for isotope separation. But, you know, these were all ideas. He never really actually built anything, but, you know, his ideas are really fascinating. So that about Szilard. So in a way, it's quite plausible that Szilard would come up with this clever thought experiment, which really strips, if Einstein really thought of the photon box as this argument that, you know, about like the possibility of measurement, it's a very involved and clumsy way, right? It involves relativity, it involves the energy-time uncertainty relation that has a very weird status in quantum mechanics. So it has a lot of sort of formal ballast that makes it not very useful as an argument about the basics of quantum mechanics. And this mirror example is a thought experiment that very much strips all this unnecessary physical ballast off it and really gets to the basis, right? Is this possible to measure two non-commuting observables more precisely than the uncertainty relation allows? And so, that I forgot to show you, that is Schrödinger, you know, shows that Schrödinger was actually the colloquium. He makes notes about Einstein talking about the photon box experiment. But so the further development of Schrödinger's thought now is interesting to follow, right? As I said, there's these two big folders, right? So Schrödinger now starts thinking very seriously about this idea of Szilard. And at first, he's not convinced at all. He tries to disprove Szilard by showing that no such state can exist in quantum mechanics. That you know, that Szilard's idea cannot be like formalized into an explicit state of the mirror and the particle that would be allowed by quantum mechanics. And he calculates around for many pages, trying to prove that, you know, if you have an entangled state, that this claim that the variance of two non-commuting states can be smaller than allowed by the variance of the total state is not cannot be formally represented by a quantum mechanical state. And then at some point he just writes an underlined note, everything wrong, right? Full stop here, everything wrong. This does not work. And it's not quite clear whether he stopped out of frustration or because Szilard actually showed him a counterexample. And so a little bit later, he says explicitly that Szilard gave him a state that fulfills this requirement. It's this state here. And if you've read the EPR paper, this is pretty much exactly, or is a bit more general form of the state that Einstein-Podolsky and Rosen use, right? All that you have additionally is an overall momentum, right? That's expressed here by this pre-factor, and a form factor that makes it more physically realistic, right? Because in the EPR case, you have an integral of over all possible momenta, so you have you know, an infinite range of momenta. But otherwise, it's exactly the Einstein-Podolsky-Rosen state. So Szilard already had that. And Schrödinger now uses this state and what he's learned now from, like, you know, really doing a lengthy theoretical study of what, you know, the characteristics of such a state. And so he actually rederives the Schmidt bi-orthogonal decomposition theorem. He generalizes the claims to a state that's not bi-orthogonally decomposed, right? If you have two observables that are not, like, you know, in which the state is not exactly diagonal, but only approximately diagonal, and plays around with all these things. And in this, you know, now realizes that the conclusion is that entanglement is not just a problem for him, for his wave interpretation, but is really a deeply puzzling thing that just as well is paradoxical for the Copenhagen crowd. And unlike Einstein, right, he does not conclude from that, okay, these two things are measurable in principle, therefore they must exist, right? He has very much already learned the lesson of the quantum mechanics and of the impossibility of hidden variables. So he never argues that this really shows that, you know, quantum mechanics simply is an incomplete theory that we could add. You know, if we now add, like, the full description of a particle, we can solve the problem. And this is, of course, exactly what he then expresses in the 1935 paper, right? He has a I think, very nice physical argument against hidden variables in this paper, much less abstract than von Neumann's argument, that. Well, I mean, von Neumann's argument is a mathematical argument, right? He very clearly says what he assumes, right? So the question is, of course, are the assumptions physically plausible or not? And in the end, they are not implausible, right? I mean, I think you can very much argue, right? I mean, basically, what you have to give up, if you give up von Neumann's assumptions, is non-contextuality, right? I mean, that's what it comes down to, right? That he assumes that quantum mechanical measurements are non-contextual. So yes, you can say we give that up, but you know, it's not like it wasn't. Von Neumann was not correct. He was just making certain assumptions. And of course, similar assumptions are made by Schrödinger too, right? I mean, his argument is about, or one of his arguments is about angular momentum. He says, you know, angular momentum is quantized, but we can define an angular momentum about every point in space. And so if you want to assume that particles have definite values for position and momenta, right, this cannot possibly be, right? We cannot possibly have a quantized angular momentum if, and that of course is again this assumption, right, if it depends on these real values of position and momentum. But again, right, that is an assumption of non-contextuality, right? You could of course say it doesn't matter what values of position and momentum it has, the angular momentum has nothing to do with position and momentum. So Einstein, as I said, comes to quite different conclusions from this. Question now is how much really Einstein knew from all that, about all that stuff that Schrödinger wrote about in these notes. But as I showed you before, Schrödinger writes about many discussions they had. So I assume, right, it's not implausible to assume that Einstein heard at least a lot of the things that Schrödinger writes about, and especially that Einstein also learned about this state that Szilard gave to Schrödinger, right? And that it's no coincidence that he uses in 1935 exactly this state without giving any credit to Szilard. But I think it's very plausible to assume that's where he had it from. Also, still in 1935 in the correspondence, Einstein freely admits that he doesn't understand Schrödinger's arguments against hidden variables, right? He writes that very, very casually. And so he doesn't see any reason to abandon this idea that, you know, quantum mechanics is just simply an incomplete, i.e. a statistical theory, right? It's a statistical summary of an underlying mechanism, and once we find that mechanism, then everything will be fine. Whereas Schrödinger remains deeply skeptical and is sort of never has really a positive answer to how to solve the question. So one last nice quote, right? He's really sort of, for our modern understanding, really the only one in the whole crowd. Neither Einstein nor his the mainstream Copenhagen guys really acknowledge this problem in the way that he sees it, and so he gets rather frustrated and writes to Wolfgang Pauli, which he has a very nice, very friendly correspondence, even though they are on totally opposite sides in this case. So he says to Pauli then responds to the case, also sort of dismissing it as something long known and not really problematic for quantum mechanics. And so Schrödinger responds, "This is how everyone I have spoken to about it thinks at first, because they all have well learned their Copenhagen credo in unum sanctum. 3 days later, they usually come back with, what I said recently was naturally quite wrong, much too complicated. Or, like Szilard, I must first think over what I should forbid you. But I have not yet received a clear explanation of why everything is so clear and simple," right? So basically the reaction of everybody is, right, yeah, we've known that long ago, it's not really a problem for quantum mechanics, but then, once they're squeezed a bit, then things turn out not to be quite as simple. So that's basically my story. As I said, I mean, we shouldn't only credit Schrödinger for being the one who coined the word entanglement, but he's also really done very important work on the phenomenon of entanglement. And I think it's fair to say that he really was the only one in his generation that realized what a deep and mind-boggling phenomenon it really is. So, one quote from his 35 paper, "I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces an entire departure from classical lines of thoughts." Okay, thank you. So now I'm turning off the record.
When was it realized finally that actually the electron and the proton in the hydrogen atom, or the solution by Schrödinger, are already entangled? Two electrons in Pauli's solution of the helium atom are entangled.
Yeah. Definitely example, right? Because there it plays really an important role. So, I mean, I think that is why everybody said, we already know that, right? Everybody uses entangled states all along, right? But since everybody thinks of it in terms of statistics, right, they just see entanglement as a form of statistical correlation. So it's just a statistical correlation, right? Of course, the probability of one thing depends on the probability of another thing. No big deal, right? Born, for example, maintains that position till the bitter end, right? There's endless correspondence between both Born and Schrödinger and Born and Einstein, where they say the same thing over and over and over again, and Born just does not see any problem in that.
And maybe because I have to leave now. Maybe I can ask a second question.
Sure.